Chris Hogan will be talking on patient safety and infection control. He is a PhD in his engineering, environmental and chemical engineering from Washington University. He presently works with University of Minnesota, professor in Department of Mechanical Engineering. He is well known in the industry for his filter, a new filter which he has innovated. And he is also postdoctoral research associate. He has been awarded a lot of honors and awards: Japan Society for Promotion of Science and Short-Term Faculty Fellow, National Science Foundation Graduate Research Fellow, and he is also editor of Journal of Aerosol Science, editor-in-chief and present now, and he is on the lot of editorial boards. Mr. Chris Hogan, who will speak on patient safety and infection control, very important aspects of the future. Over to Chris, please.
Hello, everyone. Thank you for the opportunity to speak today. My background is in aerosol science and air pollution, and I want to talk to you a bit about technologies that we can use, which are modular, to protect both healthcare workers as well as patients from infectious airborne hazards. And when I say airborne hazards, I refer to droplet transmission as well as potential for aerosol transmission. The difference actually being somewhat arbitrary. I mean, anything that could possibly travel by infection through the air or through the air and then deposit with later deposition. So it is kind of a wide swath of modes of infection. The United States Center for Disease Control, in talking about reducing hazards in the workplace, including infectious disease, has developed a hierarchy of control. If we look at the top of the hierarchy, this is considered the most effective way of reducing hazards, and at the bottom is the least effective way. Of course, the top is just elimination, which is not usually an option in the case of infectious disease, nor is substitution. And so what we're left with are engineering controls, isolating people from hazards, both patients and healthcare workers. Administrative controls change the way that processes occur. And really the last resort is personal protective equipment, or PPE. In current healthcare settings, certainly in the United States, as well as other countries, the two things that you will see along these lines, for PPE, you will see a diverse array of technologies. The difficulties with PPE are the following. They apply to just single individuals. They are not reusable. They don't mitigate infection. They delay it until the moment when the worker is taking off the PPE. And it lends themselves to shortages. Everything that this example healthcare worker is wearing, you can end up with a shortage which can be critical to the operation of a hospital. Everything from hairnets to gowns to masks can be in shortage during times of a pandemic. The converse is the negative pressure room. The negative pressure room isolates an individual patient. It does not provide protection once someone enters the negative pressure room. And negative pressure rooms themselves are expensive to operate, they're expensive to build, and they're usually limited in any hospital network. You might have 2 to 3 per hospital. And where we can think about in terms of modular hospitals in the future are instances where we work at an intermediate scale between these two types of engineering controls. So intermediate scale engineering controls refer to things which are much, much better than PPE. They will protect multiple people, multiple patients, or multiple healthcare workers. But they are smaller and more modular and more portable than negative pressure rooms. And the goal is to isolate people from infectious hazards. My own particular focus happens to be hazards which travel as droplets or as aerosols, so in the air, but they don't isolate people from the patients as the negative pressure room does. We'd like to see situations in the future where we go from PPE as a secondary source of protection, but not a primary source of protection for healthcare workers or for anyone in a hospital environment. When we move away from PPE, there's the potential to actually be even more protective. The gold standard for personal protective equipment from airborne hazards right now is the N95 respirator in terms of PPE. N95's name, or KN95, depending on the country, is required to collect 95% or better of all particles that are potentially inhaled. But what this means is that 1 out of every 20 particles is transmitted. Meanwhile, HEPA filtration, which is very common and can be employed in these more modular systems, has to meet the requirement of only 3 out of every 10,000 particles can be transmitted through. So it's actually an orders of magnitude improvement, not a slight improvement. And then we want to move to, with infectious particles, we want to move from an environment where we have collection to actually true inactivation. Collection doesn't prevent infection, it changes the potential mode of infection. Collection, we still require inactivation on the surface where the infectious particles were collected. So we'd like to move to inactivation. So to provide you some examples of existing technologies right now that can do this, I want to highlight different things. We can begin with the idea of how patients even enter the hospital if they believe they have an infectious disease. This is something we've implemented at our hospital networks in Minneapolis, Minnesota, but it was inspired by innovation that we saw in Kerala, India. The start of the COVID pandemic, Kerala instituted a number of testing booths where patients could walk up to them. Our own little twist on this was to provide an extra level of protection to the healthcare worker, where we have a fan filter unit in the upper right, and we're actually pushing in clean air. So this is a positive pressure environment. The healthcare workers doing the COVID test in this case are exposed to what is essentially particle-free air. It doesn't matter if there are patients with an infectious respiratory disease outside, the healthcare worker is protected. What this means is that the PPE, the personal protective equipment that the healthcare worker is wearing, is now a secondary mode of protection. What's truly protecting them is the fact that we have approximately 1 air change rate per minute inside this device, and it is about the cleanest air you could possibly breathe. This prevents constant need to replace PPE. For example, we did change the way people work. Instead of 1 healthcare worker doing tests, there are actually 2. Once the patient leaves, a second healthcare worker comes in, will take the test away, and will clean the front surface. No healthcare worker needs to be exposed to the patient's airspace directly, but at the same time, we can provide the level of care needed. We can also think about doing this in the hospital. Negative pressure environments do not need to take up an entire room. We can actually take devices which have been adapted from the chemical industry as well as the industrial kitchen industry, which are designed to protect people from airborne hazards. In the latter case, it's inhalation hazards such as chemicals or high concentrations of particles. And what we can do is we can design hoods where a patient actually can lie down. This can be placed on any sort of bed. And what we can have is we can have a negative pressure environment such that the patient's respiratory secretions are protected. These devices have been tested. We can show that we can collect over 99.99% of particles which a patient exhales. And in doing so, we can create these modular negative pressure spaces. What was talked about in changing and isolating sections of the hospital for patients with infectious disease from those without. This is the type of technology we can adapt. And then finally, looking into what can we do in our actual building space. Right now, ventilation systems largely utilize filters. One of the things we can think about modifying use of filtration to is the use of UV light. UVC inactivation is a very traditional technology, but certainly an underutilized technology. And one of the things we've been working on is actually testing ducted UV units, which are applicable in ventilation systems. And we've shown that they are very successful in inactivating coronavirus. This happened to be porcine respiratory coronavirus, but in terms of UV susceptibility, most coronaviruses are expected to be similar. And this log reduction of close to 99.99% for all infectious particles passing through the device is quite good. So these are the types of technologies we can think about implementing in future hospitals. I'll end my presentation there. And again, thank you for the opportunity to tell you a bit about technologies that are out there.
Thank you very much, Chris. It was very, very informative. what you have been able to decipher and things?
In India, people reach out to doctors in their near vicinity at their clinics. What protection should future clinics have?
I think future smaller clinics can consider these more portable negative pressure or positive pressure environments, both for first contact with patients, as well as, say, in a waiting room type area. These aren't overly expensive to build really in any environment. And most clinics that are existing can be adapted to do these types of things. The major bottleneck is probably just training and working with such equipment and getting both workers and patients used to them.
Thank you.